Hello everyone, and now I'm going to talk about models of orbital overlap and sigma and pi bonds, as well as orbital overlap diagrams, also known as hybridization drawings. Okay, so first things first, let's just talk about the different models of how those orbitals interacting can be discussed. Okay, so the first thing I want to talk about is a sigma bond. And a sigma bond is literally when two orbitals overlap and literally touch each other. Okay, so that could be represented visually by saying, all right, here's a hybridized orbital, here's another hybridized orbital. They're literally touching each other. Okay, you are going to find this type of bond, a sigma bond, in single bonds. All right, single bonds, all that they have is a sigma type of bond, so literal orbital overlap. The other type of bond that you can get within our different types of bonds, single, double, and triple bonds, is you can get something called a pi bond. And that is not literal orbitals touching each other. A pi bond results from unhybridized orbitals participating in a chemical bond. And so basically what you're going to see visually when we draw this out is you're going to see two orbitals that are not touching each other at all, but they're still going to be able to share electrons between them. So typically we see that like this, those two orbitals are not touching each other at all, but you're going to see some sharing happen between them. Okay? A sigma bond, or a single bond, excuse me, only contains sigma bonds. So single bonds are sigma, and that's our symbol for sigma. A double bond is going to contain one sigma bond and one pi bond, and a triple bond is going to contain one sigma bond and two pi bonds. So quite often you might be asked to look at a molecule or draw it out and then ascertain how many sigma bonds exist in that molecule and how many pi bonds. And it's super, super easy. All you have to do is look at your bond types and count. All right, so let's look at these two molecules over here that I have already drawn out. All right, so our first example is ethane. Ethane looks like this. All right, the only thing I see in ethane are single bonds. I see 1, 2, 3, 4, 5, 6, 7 single bonds. So I'm going to write that down, right down here, 7 single bonds. And I know, because it's in my notes, I just told you, or you should know, that single bonds only contain sigma. So what that means is that there are 7 sigma bonds in this molecule because there are 7 single bonds there. Okay? But if I look down at ethyne, I do not only see single bonds. I see 2 single bonds and a triple bond. So just based on the fact that there's 2 single bonds there, I know there's at least 2 sigma bonds present because I know that every time there's a single bond, that means there's a sigma. But let's look again at what triple bond means. Triple bonds do contain a sigma bond, but also they have 2 pi bonds as well. So basically what I'm telling you is every time there's a bond in general, there's a sigma bond. But if you have a double or a triple bond, that means that there might be pi bonds as well. So I see 3 bonds present, which means that there's going to be 3 sigma bonds in this molecule. But I also see this triple bond right here, and that tells me that because it's a triple bond, there's also going to be 2 pi bonds as well. Okay, so evaluating molecules for how many sigma and how many pi is super, super easy to do. Again, you just have to count your bonds and look at what they contain. So for this practice problem down here that has to do with sigma and pi, then now would be a great time to pause your video and just count your bonds in cyclopropane and in propene and see if you get what I get, okay? But if you don't want to do that and you're not comfortable, keep watching. In cyclopropane, I do not see any double bonds. I do not see any triple bonds. So that means that the only bond type present is going to be sigma bonds. So I just have to count to see how many bonds I have. Now I'm going to count real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9. I count 9 single bonds, which means there's going to be 9 sigma bonds in this molecule and nothing else, because I do not see any double and I do not see any triple bonds. For propene, on the other hand, I do see a bond type other than a single bond, but I know that every single bond type has 1 sigma bond in it. So again, I'm going to count my bonds. I see 1, 2, 3, 4, 5, 6, 7, 8 total bonds, which means there's going to be 8 sigma bonds in this molecule. And then that double bond right here means that there is also going to be 1 pi bond in this molecule. All right, so that's easy peasy. The orbital overlap or hybridization drawings, on the other hand, are a little bit harder to do, but I will walk you through it. And in case you forgot that I said this in class, they are extra credit on your test. I will not be requiring you to learn how to do orbital overlap drawings. The AP test will not be requiring you to do orbital overlap drawings, but if you want to learn it, it is extra credit, so I'll walk you through it anyway. When we are looking at our structure, we want to see what the hybridization pattern is on every single atom that's in the middle, right? So in this case, I have 2 carbons that can be considered my central atoms with molecular geometry. So if I look at my VSEPR chart, I can see that this carbon on the left and that carbon on the right both have similar geometry because they are both bonded to 4 things, right? This carbon has bonded to 1 hydrogen, 2 hydrogens, 3 hydrogens, and then the other carbon. So if we look on our VSEPR chart, we know that that is sp3 hybridization because the molecular geometry on that carbon is tetrahedral, and tetrahedral means this type of hybridization, all right? The other carbon over here is going to be the same hybridization because, again, it is bonded to 1, 2, 3, 4 total things as well, all right? So keeping that in mind, I'm going to redraw only my atoms on the right-hand side to start with. Not any of the bond lines, just my atoms. So I have those 2 carbons, and then I have my hydrogens. My hydrogens are super, super easy because hydrogen has an electron configuration of 1s1, which means it does not have more than one type of orbital that could potentially hybridize, so we are just going to represent hydrogen's orbital space as normal. And I'm going to represent it with these little green circles. Hydrogen has 1 electron that floats around it at any given time, so I'm just going to draw those like this. All right, now we got to talk about carbon. Carbon, we agreed that they were both sp3 hybridized because they are bonded to 4 things, okay? So if you recall from the other video, when carbon is sp3 hybridized, it has that little group of 4 hybridized orbital spaces. All right, and those orbital spaces, since we agreed that this was sigma bonds, are literally going to reach out towards the hydrogens and the other carbons. I'm going to draw that in for you. Here's one of them. Here's one. Here's one. And there's one. And I'm going to use a different color to represent carbon's electrons so that we can see the difference. All right, it has 4 unpaired electrons in that hybridized state, so I represented them for you. All right, the other carbon has the exact same pattern of hybridization, sp3, so its hybridized orbitals are going to reach toward everything else that's there. And that one ended up being a little bit longer, but That's because I'm bad at art, not because it's actually longer. And let me represent its electrons as well. Okay, so that is the orbital overlap diagram of ethane. And it looks super, super funky, but it is just another way to look at Lewis structures and look at what's going on with those electrons. So we can see the sigma bonds, right? And a sigma bond is, once again, when two orbitals are literally overlapping. So I'm going to add in yellow, we can see all those areas of orbital overlap. We can see one here where there's orbitals are overlapping, so that's one sigma bond. We can see it here for another. We can see it here. 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 And we can see it there. So if you count all of those up, that's going to add up to your 7 sigma bonds that we looked at on the other side. All right, next example is going to be ethine, which has that triple bond. So let's look at our cool VSEPR chart and let's figure out what kind of molecular geometry it has first and foremost. We see that each carbon is bonded to 2 other things, and there are no lone pairs on that. So when we look at that VSEPR chart, that is going to be a linear molecular geometry, which means that each of those carbons are sp hybridized this time and not sp3 hybridized. So based on the other set of notes, we know that when we draw out those carbon orbitals, we're going to see the hybridized ones, but there are going to be 2 sets of unhybridized p orbitals existing alongside, and that's going to be for both of those carbons because, again, it's a different hybridization pattern this time. So I'm going to start over on my right hand side by redrawing only my atoms, not my bond lines. And then I'm going to do my hydrogens first, just like before. They still have only 1s1 configuration. They can't hybridize at all because they don't have anything to hybridize with. And I'll represent hydrogen's electrons like that. All right. Each carbon is going to have that sp hybridization. So we're literally going to see its hybridized sp orbitals reach out on either side. I'm going to draw one at a time, okay? However, because we know that it's sp hybridized, not sp2 or sp3, there's going to be 2 unhybridized p orbitals left over. And so here's one of them. I'll draw it up and down. And then the other one, draw it in. Oops. Draw that one in purple. All right. So let's just label that really quickly. This is a P. This is a P. And then both of the ones in blue are sp hybridized ones. And I'm just labeling them so that we can keep it straight. All right. Now really quickly represent the electrons that belong in those orbital spaces. I know that my sp hybridized ones are going to have 1 electron each. So there's one and there's one. And then I know that my p orbital spaces are going to have 1 each. So I'm going to put 1 here at the top of each of them. All right. So that's one of the carbons down. I'm going to do the same thing for the other because both of those carbons have the same molecular geometry. I have my sp hybridized reaching out on either side to directly touch a different orbital space. And I have their electrons, 1 and 2, right there. And then they too have an unhybridized set, or 2 unhybridized sets, excuse me. All right, I'm going to relabel them just like I relabeled already. Okay, so we've got a lot of stuff going on in this one. It looks a little bit more confusing than the last one did. We know already that there are 3 sigma bonds happening. All right, and we can see that here, here, and here, right? We can see that those orbital spaces are literally touching, literally overlapping. But what we have not yet talked about is what's happening with these p orbitals. We know that there's 2 pi bonds happening, and the pi bonds are what happens when unhybridized orbitals end up sharing electrons over distance. So, with that pink set of p orbitals, they are going to share electrons between them. So I'm going to represent that like this with a solid line between them just to represent that the electron can travel back and forth. And you are also going to see that exact same thing happening with the purple ones, with the purple p ones. I'm going to draw it in a dotted line so it doesn't start overlapping and getting more confusing with the pink ones though. So we see this, some sharing happening here, and some sharing happening there. So this one looks a little bit crazy, I'll grant you, but literally what is happening is, again, we have those 3 sigma bonds, whoops, we have those 3 sigma bonds here, here, and here, so those are the 3 sigma, and then every time you see that extension over distance between a p orbital, here's one of the pi bonds happening here, and then here is the other pi bond happening there. And so that's where our 2 pi bonds are coming in. Again, I know, super confusing, but extra credits, you don't have to worry about it if you don't want to. Going down to the practice problem, if you are pursuing drawing the orbital overlap correctly, now is a great time to pause the video and see if you can do it by yourself, but if not, feel free to keep watching. For our practice problem, C2H4 would be drawn like this, just to give you an idea of what that molecule looks like overall. I see 4 single bonds in it and 1 double bond, which means that when we draw the orbital overlap diagram, we should be seeing a total of 5 sigma bonds. And since there's a double bond, I'm also going to see 1 pi bond. So just keeping that in mind going forward. I'm going to start out just like I did before by looking at the geometry of each of these carbons. So both of these carbons are bonded to 3 things, and so if I look in my VSEPR chart, I would find that they all have trigonal planar geometry, which means that each of those carbons is sp2 hybridized. Okay, in an sp2 hybridized, that means that 3 total orbitals are going to hybridize together. It's going to be an s orbital, and 2 of the 3 possible p orbital spaces are going to overlap and hybridize together, leaving out 1 of those p orbital spaces off by itself in an unhybridized fashion. So once again, I'm going to draw just my atoms and none of my bond lines to start out. My hydrogens, as usual, are going to have that single sphere around them to represent that 1s1 configuration, and each of them has that singular electron there. Okay? My carbon atoms, on the other hand, are going to have some hybridized. In this case, again, it's sp2. So what we should be seeing is 3 hybridized spaces for that sp2 on each carbon. So I'll just draw all of those first. 1, 2, and 3. And then we are going to see 1 unhybridized p on each of them. All right, you represent carbon's electrons. 1, 2, 3, 4 on each of them. 1, 2, 3, 4 on each of them. So if we can just interpret a little bit, we are seeing our sigma bonds in those actual areas where our orbitals are overlapping. So I'm seeing that here, 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 and here for a total of 5 sigma bonds. And I am seeing those unhybridized p orbitals that are hanging out, and so they can reach out to each other over distance, and that is going to be my 1 pi bond that is present in that molecule. And I know I drew 2 lines between our top and our bottom, but remember those are singular orbital spaces even though there's 2 little bubbles, because every p orbital has 2. All right? If you have questions about orbital overlap diagrams, you really want to learn how to do it, please talk to me in class, but I hope this video was helpful.